Okay, so as we go through these, if you need to modify your answer a little bit, please do so, okay? Because this is the kind of stuff that will be on your quiz tomorrow that I will post at 3:30 today. Okay? So the idea of the atom was first proposed by whom? Democritus, right, okay? And it was rejected at the time because, well, people believed in the four elements. It made more sense. It was more applicable to their lives, and more respected people had come up with that idea. Okay? For number 2, what elements did the Greeks believe all matter was made up of? Earth, air, fire, water. Okay? It made sense because they could see that everything in their daily lives was made up of those things. It made good sense. We talked about how steam was some parts water, some parts fire, and some parts air. Okay, how mercury would be some parts earth and some parts water. Okay, it all made really good sense to them. It was something that was reasonable and logical. Okay, for number 3, during the Middle Ages, a group of people inadvertently did a lot of work to develop the science of chemistry. Who were they? The alchemists. Okay. Right, they were trying to get rich. They were trying to turn common substances into gold or make some kind of drink that would make you live forever. Okay, things that we now, of course, know are impossible. Okay. Right. During the late 1700s, a man used the data from many experiments on matter to develop an idea on the structure of matter. Who was he, and what were the points of his theory? Okay, let's go with who was he first. No?
Dalton.
Dalton. Okay, how many points did his theory have? 4. Okay, what were they? First one.
Elements are composed of tiny particles.
Okay, all elements are composed of tiny particles, or all matter is made of atoms. I mean, you can put it in your own words as long as essentially it comes down to all matter is made of atoms. Something along those lines is great. Okay, second point.
Atoms of the same element are identical. The atoms of one element are different from those of any other element.
Exactly. All atoms of the same element are identical, and then, of course, atoms of different elements are different. Okay, third point.
Atoms of different elements can combine with one another in a simple whole number ratios to form compounds.
Right. Atoms can combine in simple whole number ratios to form compounds. What's the most important part of that point? The whole numbers part. You can never have half an atom. In a chemical reaction, you will not break an atom in half or into quarters or anything like that. Okay, fourth point. Tells us what happens in a chemical reaction.
They're either joined together, separated, or rearranged.
Right, atoms can be separated, joined, or rearranged, but they are never turned into other elements. Okay, so in a reaction, I can make new things, but I can't make new elements. Okay, if I start out with sodium and chlorine, all I can ever have is sodium and chlorine. I can't magically get lead out of that. Okay, making sense to everybody? Okay. All right, for number 5, looking at this theory now, what things do you know of that can prove some of his ideas wrong? All right, well, first off, very first point, indivisible particles. Okay, are atoms dividable? Divisible, something like that. That word. Absolutely, we can do that. Okay, of course, at Dalton's time they couldn't, and because Dalton's point refers to more of the chemical nature of matter, it is still true. Okay, there is no chemical means by which you can divide an atom. Okay, there is a physical nuclear means by which you can divide an atom, but that's different. Okay, so yes, to an extent, that's not 100% true unless we look at it from a strictly chemical point of view, which is how we take it. All right. Second thing, in the second point, it says atoms. Every atom of the same of an element is the same. Not entirely true. Okay, 99% true, but every single element has something called isotopes. Okay? Isotopes are versions of the atom that have extra neutrons in them. Okay? They have the same number of protons, they have the same number of electrons, but for whatever reason, they have a few extra neutrons and are thus a little bit heavier and a little less stable than all the other identical atoms of that element. Okay? So as an example, how many people have heard of the term carbon dating? Okay, it's something that we use to determine how old artifacts and fossils and things like that are. Okay, all radiometric dating, of which carbon dating is an example, okay, uses the fact that isotopes are present in a certain ratio to normal atoms in a particular material. Over time, those isotopes decay into something else, whereas the regular elements do not. Okay, and so when we look at how much of the material that, let's say the carbon-14, that's the weird isotope of carbon that we use, we look at how much of it is left and how much of its materials that it breaks down into are present, and we can determine its age because we know how quickly carbon-14 breaks down into regular carbon. Okay, that sort of makes sense. That's how all radiometric dating works. All isotopes of things break down radioactively, right? Carbon-14 is just not something that can hurt you, okay? But like uranium, for example, decays radioactively and has a very short half-life, okay? And so it decays very, very quickly and releases radiation that is bad for you. Carbon-14 does the same thing, but it's much slower and much less harmful, okay? So you wouldn't even notice it. Making sense? So isotopes are that thing that kind of makes the second point not really 100% true. Okay. All right, other than that, the rest of it is good. Okay, describe in your own words the models of the atom discussed here. Give a brief explanation as to why each was rejected or changed over the years. Okay, do you think our current model may change and why? All right, so that one's kind of up to you. Okay, the models I would talk about would be solid sphere, plum pudding, okay, nuclear model, and then Bohr and de Broglie. Okay, so obviously with the solid sphere, we discovered electrons, didn't fit anymore. Plum pudding, we discovered protons, didn't fit anymore. Okay, nuclear model, well, didn't like the way the electrons were. Bohr model, couldn't explain the movement of electrons. De Broglie, current model, seems to explain things that we know. Okay, for right now. Could we discover something that says it's not right later? Sure, anything can happen. Okay, I mean, science has to be flexible. We have to be willing to change how we think, right? I mean, even recently, people didn't know or think that gravity could be a wave, but it is. Okay? It can travel and act like a wave, okay? A gravitational wave that we can detect now that we didn't know existed before. Okay. As our knowledge increased, we discovered the atom had smaller parts. Name these parts, describe them, and tell where they are located according to what we believe to be true now. So, what's in the nucleus?
Protons and neutrons.
Protons and neutrons. Okay, so what I'd be looking for here is like protons, positively charged in the nucleus. Neutrons, no charge in the nucleus. Electrons, negatively charged in the cloud. Okay, that would be good enough for that one. Just got to know where everything is and what charge it has. All right, number 8. If I have equal amounts of lead and carbon, the lead is much heavier. Why?
More protons in the lead.
Yeah, the atoms are bigger. Okay, we were talking about this the other day. In an atom of lead, there are 82 protons. Okay, and there are 140 something protons. Okay, it's a big atom. Whereas an atom of carbon has 6 protons and 6 neutrons. It's much smaller. So if I have equal numbers of atoms of lead and carbon, the lead is going to be way heavier because the atoms are way bigger. There's just more matter there, okay, when we're talking about something with larger atoms. Okay, number 9. Nuclear reactors use atoms with very large nuclei like uranium, which has 237 particles in its nucleus for fission. That would be the splitting of the atom, which is how we generate all of our nuclear power. Okay. Why wouldn't they use smaller, less dangerous atoms like lithium that only has 7 particles in its nucleus? Yeah, there's going to be less energy. I mean, the smaller the atom, the less energy there is holding it together. Okay? The bigger an atom is, the more energy it can release when you break it apart. And generally, the less stable they are. Okay? You look at the periodic table here, okay? All of these last ones that are here, okay? These are all like so short-lived that you basically can't even detect them. all right? And that's because they're extraordinarily large, okay? And that makes them unstable and they break down quickly. It's why they're not discovered in nature, okay? These are all produced in like the Large Hadron Collider, okay? And things like that. So they don't really exist in nature. But something like uranium does, okay? And, I mean, strictly from the, you know, practical standpoint, it's way easier to hit something this big than something this big, okay? It's, you know, simply a matter of being able to hit your target, right? All right, so the way a nuclear reactor kind of works, just so you get the idea here, is in a typical fission reactor, you're going to have fuel rods, and they're exactly as the name would sound. They're a metal rod that embedded on the surface are pellets of enriched uranium. Okay? And what happens in a nuclear power plant is these rods are lowered into water. And then an emitter emits free neutrons towards the fuel rod. When those neutrons hit the uranium pellets, they cause the uranium atoms in the pellets to split. That's the process of fission, splitting the atom. Okay? When that happens, the pieces of the split atoms will go off and hit other atoms and they'll split. And as long as you don't expose too much of the rod to the neutrons, you can control the rate of the reaction. Okay? When that reaction takes place, lots and lots of heat is generated, which evaporates the water into steam, and the steam drives a turbine, and that's what makes the electricity. Okay? This can become a problem if too much of the rod is exposed, all of the water evaporates, okay, or something like that, and then you have a meltdown. Okay, it's what happened at like Chernobyl and things like that. They just, the rods could not be removed, all the coolant was gone, and it just kept going, and they couldn't make the reaction stop. Okay? Even stopping the emitter at that point wasn't enough, because all of the atoms were already breaking apart, and their pieces were going off and hitting other atoms, and there was no stopping it. Okay? That, incidentally, is how a nuclear bomb works. Now, I'm going to show you how a nuclear bomb works. Okay? Now, in the like most basic sense, this will not help you make a bomb. Okay? Mostly because it's not detailed enough, and thankfully you can't get your hands on the stuff you need to make one. Hopefully. Okay? So, what generally happens in a fission bomb is there is a casing that is made of high explosive material. Okay? That is usually like plastic explosive, C4, okay, you know, something like that. And in the middle of this is basically a lump of fissionable material, plutonium, okay, something like that. So a nuclear bomb is actually two explosions, one very small one and one very big one. Okay? So what happens is this casing is detonated, and because of its shape, the particles produced by the explosion are focused inwards towards the fissionable material. So rather than having an emitter, you just have this explosion that shoots debris down towards the fissionable material. When it hits it, it starts a chain reaction. Okay, so the plutonium atoms break, and their pieces go off and break other plutonium atoms, and pretty soon there's a mushroom cloud and untold destruction, and yeah, that's generally how it works. Okay, but it comes down to big atoms have a lot of energy stored holding them together, and if you break them, that energy is released as heat. Okay, and that's what we can use to either cause untold destruction or generate electricity. Either one. Right? And more recently, we've even started now with fusion, which obviously works differently. That's forcing like hydrogen atoms together to form a helium atom, which is how the sun works. Okay? So it's kind of the opposite of breaking the atom. It's actually making bigger atoms out of smaller ones. That's much more difficult to do in a controlled way. Okay? And in fact, they just recently had the first time where they had a break-even fusion reaction, where they had a controlled fusion reaction that actually made as much energy as was required to cause it. Okay? Before that, we never really were able to do that. It always took more energy to make it happen than we would get out of it, which is like not practical. Okay? But we're kind of getting there now. All right, number 10, atoms are indivisible. Why was this statement believed for so long? Because nobody could do it. Okay, I mean, that's the most logical answer for that. That's why people said you can't break the sound barrier. Why? Because no one's done it yet. Yet, okay, was the key word there. Okay, so why is it still true, provided no human technology is present? Well, it actually isn't. Radioactive materials break down on their own. Okay, now it's not like a massive splitting of the atom, but it's a slow kind of decomposition of the atom, okay, over time. But generally, yes, in a chemical sense, we can't break an atom. Okay, from what you know of the structure of the atom, how does it stay intact? Why do the electrons not fly off? What keeps the electrons orbiting the nucleus?
They want to try and make a positive or a neutral charge, so they're like drawn to the nucleus.
Exactly. They're attracted to the nucleus because the nucleus has the opposite charge. The protons are there, they're positive, electrons are negative, so they're naturally attracted to their opposite. Okay? And then even within the nucleus, if you've got the most positive thing imaginable and it's next to something neutral, well, that neutral thing by comparison to that positive thing seems almost negative, and there's this atomic force, strong atomic force that actually holds the nucleus together as well. Okay? All right, and then number 12, we were talking about this. This is the basis for de Broglie's cloud model. Okay. Oh, that's not good. And so basically it makes glow-in-the-dark materials work. That's the electrons getting excited, and they move away from the nucleus. Okay, and then when that light is removed, okay, the energy starts getting given back, and the electrons fall down, so they glow for a short period of time as the electrons fall back to the lower energy levels. That's also how photosynthesis works. In the chlorophyll molecule, the electrons get excited, they move away from the nucleus, and then when the sun goes down, those electrons fall back down, and the energy they give off is used to break apart carbon dioxide and water and turn it into sugar. Okay, so it's a pretty important property of electrons and matter for that to work. Okay, all right, questions on any of those? Okay. All right, I'm going to give you guys about a 5-minute break here within the classroom, and then we'll get started on naming compounds, okay, which for today will probably be mostly review. Okay, so what we're going to look at today is naming essentially the two types of compounds that we're going to deal with most often, right? And that's going to be ionic and molecular. That's going to seem familiar because in Science 9 you learned how to name simple binary ionic and molecular compounds. Now, we're going to build on that a little bit with the ionic compounds, because there's a few exceptions that you wouldn't have gone over in Science 9 that are important in Science 10. So at the start at least it's going to seem familiar, and then there'll be some new stuff after that. So, if a compound is ionic, what is it made of? Anybody remember? A metal and a non-metal. Okay, so what that means is it's made from something on the left side of the periodic table. Okay, the left and right side is divided by the staircase here. Okay, so everything on the left side is a metal, and everything on the right side, okay, is a non-metal. So an ionic compound is something from each side. Okay, a molecular compound is made up of only non-metals. So both things are from the right. Okay, everybody with me there? All right. Now's as good a time as any to give these up. All right. So if we're talking about ionic compounds, as we said, an ionic compound is made of something that is from the left side, a metal, and something from the right side, a non-metal. Okay? Now, ionic compounds are quite different from molecular compounds, not just because of what they're made out of, but because of how they bond together. Okay? An ionic bond is actually very weak and very impermanent. Okay? Because it involves trading electrons. Okay? So metals generally want to give away electrons. Non-metals generally want to take them. And the reason for that is they're trying to make their outer shell of electrons full. Now this goes back to Bohr's model. This is why we still use Bohr's model a little bit, because it does help explain some of the things that go on in chemistry. Okay? If I am looking at an atom of sodium, okay, so in the nucleus of a sodium atom, okay, there are 11 protons, okay, and there are 12 neutrons, okay, and there are 11 electrons. Now, according to Bohr's model, there are shells or energy levels that electrons can be found in. The first orbital can hold 2, or the first shell, okay, and the next shell can hold 8. And then the next shell can also hold 8, but there's only 1 in it, because sodium has 11 electrons. Okay? So what all atoms want to do is have their outer shell full. Okay? So what would be easier for sodium to do? Pick up 7 electrons, find them and hold on to them, or give away 1? Yeah, it's totally easier to give away 1. Okay? And most metals are like that. Okay? Their outer shells are less than half full, so it's easier for them to give up electrons than it is to find more and fill their outer shell. It's easier to give it away and then not have that shell at all. The one below it is full already. Okay? So sodium needs to get rid of 1 electron. Chlorine, okay, by comparison, is a nonmetal. It has 17 electrons. So its outer shell has 7 electrons and is only capable of holding 8. Are these two going to get along? Very much. They each have what the other needs. Okay? Sodium needs to get rid of 1 electron. Chlorine needs to pick up 1 electron. Okay? So these two things will form an ionic bond where sodium will trade its electron and just give it away to chlorine. Okay? Now, don't read into this too much in terms of a social commentary or context here, but after that, there's not really any reason for them to stay together. This is the part I don't want you to read the social part into. Okay? They got what they wanted, and now there's nothing keeping them together. So they split really easily after that. Okay? So if I take an ionic compound like salt and I put it into water, does it dissolve pretty easily? Okay. When it dissolves, it actually breaks apart. And I've got positively charged sodium ions floating around. I've got negatively charged chlorine ions floating around because they have what they want. Sodium's positive now because it lost an electron. Chlorine's negative now because it gained 1. But they both have a full outer shell, so they're really happy. But they don't have to be together to be happy. Okay? No, that's awful. Just don't forget about the happy part. It's just that's kind of the analogy we use. Okay? So that's what happens in an ionic bond. An ionic bond just involves getting what is needed, and then that's it. Okay? So they're very weak. They can split very, very easily. Okay? Everybody with me on that? That's really all you need to know about an ionic bond. It involves a trading of electrons, and they're weak. Okay? All right. So when we want to name an ionic compound, okay, we want to name the metal first, and then we want to name the nonmetal second, and we want to change the nonmetal's name so that it ends in "ide." Okay, so if sodium and chlorine go together, they would make sodium chloride. Okay, does that ring a bell for everybody? Okay. Right, so that's the general rule for writing the names of ionic compounds. Okay, write the metal first with its name unaltered, and then we write the name of the nonmetal, ending in "ide." Okay? Do we use prefixes in an ionic compound? Like would I ever say like sodium monochloride or calcium difluoride? I don't. I only use prefixes for molecular compounds. Okay? The reason we don't use prefixes for ionic compounds is there's only one way that a metal and a nonmetal can go together based on their charge. So I don't need to indicate how many there are. How many there are is a given. Okay? So for sodium, okay, sodium always has a +1 charge. If you look on your periodic table, okay, you can see that for the metals, their charges are actually listed in the boxes. Okay? That's not true for all things. Okay? But everything in group 1 is +1. Everything in group 2 is +2. Okay? Everything in group 3, +3. Breaks down a little bit from there. Okay? When we go over to the nonmetals, okay, it's a similar thing, but we don't, for some reason, write the charges in the boxes. Okay? But if we start over here, at the far right-hand side, these are the noble gases. They all have a charge of 0 because they have their outer shell full. Everything in this column, so column 17, or group 17, has a -1 charge, okay? Because they can pick up 1 electron. Everything in group 16 has a -2 charge because they can pick up 2 electrons. Everything in group 15 has a -3 charge. Okay? They can pick up 3 electrons. And you don't need to really go any further than that because then it gets weird. Okay? But that's the consistent rule. Okay? Everything in group 17 is a -1. Everything in group 16 is a -2. And everything in group 15 is a -3. Okay? All right, so sodium is a +1, and chlorine is a -1. So do they perfectly balance each other? Yes, they do. So that's why I don't need to put in a prefix. There's only one way that these two things can go together and have the charges work out. Okay? It's why you do the drop and swap. Okay, when you're doing the formulas, okay, is to make the charges balance. Okay? So similarly, if I was to put magnesium, which is a +2, with fluorine, which is a -1, how many fluorines do I need to make this work? 2, which is why when you do the drop and swap, the 2 would go here and the 1 would go there. Okay? There's only one way magnesium and fluorine can go together so that the charges balance. MgF2. That's why I don't have to put a prefix in there. There's only one way they can go together. Okay? With molecular compounds, they don't try to balance the charges. So nitrogen and oxygen can go together in any number of combinations because they're going to share their electrons. That's why we have to use prefixes for molecular ones. We actually have to say, in this particular combination, it's this many and this many. Okay. All right, that's ringing a bell? The drop and swap? Okay, so the rules for naming, okay, we already went over those, okay, is that we simply name the metal first, non-metal second, and something that often comes up is this. Names of chemical compounds are not proper names. Not like John Doe here, Jane Smith. They're not a proper name, so I don't capitalize them. Okay? Sodium chloride is written with all lowercase, unless you're starting a sentence with it. Okay? Then of course you would capitalize the S on sodium. Okay? But because it's not a proper name, it shouldn't be capitalized. I'm not going to mark it wrong if you do, but just know that the convention is they're not proper names, so they shouldn't be capitalized. Okay. All right. And the big thing here, a true compound, okay, ionic compound, should have a net charge of 0. So that means the negatives and the positives have to work out. Again, that's why you do the drop and swap when you're writing the formulas for chemical compounds. Okay? That works out in the reaction that we have here, because aluminum is a +3 and chlorine is a -1. Okay? So I would totally need 3 chlorines so that I'd have 3 negatives and 3 positives. All right. So we've already done this one because I used it as an example, so you don't have to do number 1. I want you to write the names of those other 3. Okay, so you can use your periodic table. Okay? I'd like you to write the names of those 3. All right, so for number 2, okay, we've got K with F. K stands for potassium. And that's our metal because it's listed first. We always write the metal first. Okay, and F stands for fluorine, which I will change to an IDE ending, fluoride. Okay, potassium fluoride. We're all right with that. Okay. For number 3, this one sometimes gives people trouble because hydrogen is a gas, but it's also a metal. Okay, hydrogen is in fact the most metallic thing there is. Okay, but it just has an incredibly low boiling point. Okay, so it actually is a gas at room temperature, but it is a metal, so it's listed first. This stuff would be hydrogen iodide. Okay, now, weird thing about hydrogen, it is the simplest atom. Gaining or losing 1 electron gets rid of its outer shell. It actually would then have no electrons and have just 1 proton to be positively charged. But remember, that first shell can only hold 2 electrons. Could it also pick one up and have a full outer shell? It could. Hydrogen doesn't normally do that, act as a nonmetal in an ionic compound, but it can act as a nonmetal in molecular compounds. So if it is in a molecular compound, it will be listed second. Okay, it does happen sometimes. If hydrogen is listed first in a compound, as it is here, it's behaving as a metal and it's ionic. But if I have a compound like this, hydrogen is behaving as a nonmetal because it's not listed first and there's a nonmetal coming before it. Okay, so it's just something to watch out for because hydrogen's kind of weird. Okay, and it can act as a metal or a nonmetal. Okay, and then our last one, we got CaBr2. Ca stands for calcium, and Br stands for bromine, but we want to make it end in ide, so calcium bromide. Do I need a dye in there? I do not. That's the only way that calcium and bromine can go together. Okay, so it's just calcium bromide. Ionic compounds do not get prefixes. Okay. All right, let's have you do 2 more and we'll call it a day. Okay, so for number 5, Al stands for aluminum. I refuse to pronounce it as it's been recently designated. Okay, it's actually now aluminium, which sounds like really cool, but I just can't bring myself to say it. Okay, so it's aluminum aspartide for this one. Okay, and then for our other one here, CS is cesium, and S is sulfur, so this would be cesium sulfide. Okay. You have a quiz tomorrow. I will post it right after school today. Make sure you have a look at it. It's on the atom stuff. Okay, there won't be any naming on it, just the atom stuff. All right, good work today, guys.